Okay, the other type of circuit that was proposed is the CPL. And just to remind you, what's a CPL? We have studied in the DIC class the implementation of multiplexer using pass gates, right? So this is a select line. This is the select prime. Okay, and let's say for this example, this is A, this is B, and this is the function. And so the function is when select is 0, we choose B, okay, which is right here. And then when the select is 1, we choose A. This is called pass logic, okay, because we use the NMOS the NMOS to implement the function. Now, if we implement the function and its complement like so, the function and its complement, we call it complementary pass transistor logic. Okay, so if we implement the function and its complement, we call it complementary pass. The value of this complementary pass logic is the fact that you gain implementing the function and its complement, and in many cases we need the function and its complement. In many cases, in many um, circuits, we would like to have always the function and its complement, but it comes at a price, which is 40 transistors. And one thing we know about the pass gate, that it doesn't give you a full VDD here, rather it gives you a VDD minus VT. But because we are implementing the complementary, we can boost the output from VDD to VDD with this tiny PMOS, and this tiny PMOS is activated by the negative or the complement of the function. So is this node as well. Now, if this node needs to be at VDD, it will be through the NMOS as VDD minus VT, right? So we can boost it through this PMOS. So the complementary pass logic has two features. The very first feature is that I have the function and its complement. The second feature, it boosts the output, the high output from VDD minus VT all the way up to VDD using these PMOS pull-up transistors. Okay. All right. Now let's take a look and go to the whiteboard here and analyze this circuit a bit more. So you can see here, and this is the complementary pass logic, the CPL. So for example, here, if you look at the sum and the sum complement, typically the output is obtained after an inverter. Okay, so before the inverter, the sum is generated from a sum prime, and the sum prime is generated from a sum signal. Now, for instance, if we take a look at how this is generated, we can see that the sum signal, you can see that I can arrive to this point, okay, through various paths. So for example, I have for example, let's see, so if we take a look at, I wrote earlier the sum equals a b c, or a prime b prime c, or a prime b c prime, or a. So let's see if we can obtain these terms to generate the sum. So you can see here the ABC that can be obtained. This is through this path. This is ABC, meaning that if A is 1, B is 1, and C is 1, this node will be charged to high. And I can obtain the A prime B prime, which is this term here, okay, A prime B prime C, A prime B prime C, through this pattern, A prime and B prime, okay, and C prime, okay, through this path. Okay, so this generates for me a high voltage value at the output sum, and I can obtain this term here, which is a prime B C prime, A prime B C prime, A prime sorry, A prime, B, C prime, like so, to the output, which generate this term. And finally, I can obtain the A, B prime, C prime, the A, B prime, and C prime through this path, to the output. All of them will generate here a value of high or logic 1, okay, if any of those terms are correct. Okay, similarly, you can see how you can do this for the S prime. Okay, so now you can see how we generated the function, and now the S prime and the S, let me use black here. So the S prime or the S, they go through inverters to generate the sum and sum prime. Also watch these pull up PMOS transistor, so that the VDD minus VT is pulled all the way up to VDD. Now, why VDD minus VT? Well, because we are charging through NMOSes, and we have learned from DIC class that the NMOS is a bad charger. It will charge all the way to VDD minus VT. Okay. So similarly, we can do the same discussion for the C out. Okay. So here is the C out signal. Before the inverter is C out prime, and here's C out prime, and here is C out. So let's say, for example, the C out. Can I get these terms for the C out signal? Let's see. Okay, so here is what? Here is BC. Okay, so I got BC, or, and here is A. I've got here A. Let's see. Let's choose another color here. I've got here from the A, I can go through the output from one path, A, B prime, C, A, B prime, C, A, B prime, C, and I can go to the output through A, B, C prime, A, B, C prime. Okay, all right. And that's about it, I guess. Notice that I can. This is the signal, and I can generate from these these missing terms. So now you can see this is the BC. It is right here, BC. I'm left with the AB, all right, and AC to generate, but they can be generated by these two terms, by Boolean manipulation. In fact, to double check what we are seeing, we can, if I use the eraser here, um, we can look at the K map. Okay, so here's the K map, all right, and double check what I said. Okay, so this is A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, and oops, oops, and this is 0, 1. Okay, and now you have here BC. Let's fill those. BC, here is BC, right, and A, B prime C, A, B prime C, which is this one, and AB, C prime, AB, C prime. And if you minimize those, right, logic minimization, you get this. Okay, so whatever generated here is C out. Now here's a question. We have analyzed the circuit, and what is this now? Well, this is the reason for this is to pull the output, which is C out in this case, to 0 when not charging output to VDD minus VT, obviously, or to VDD. Let's leave it that way. Okay, so when is that? Give me an example. It's one of those. For example, take for example here the case when you have 0, 0, 0, this case here, where I'm supposed to get a 0, you will see that there is no path. This node will be left floating, okay? And therefore, we have to provide a path to 0 to it. So to avoid having a floating node, right, in my design, and this is the case here as well, by the way. So what you do, you connect that that uh, pattern of inputs that might generate floating node to 0. Okay, so we need to pull this down all the way to 0 so that we don't leave it to floating. Okay, okay, so pull the output to 0 when the output is not charging. Okay, and I would like to continue to avoid to avoid to avoid floating node or floating output. Okay, all right. So this is the case for the circuit design for this type of logic, which is the pass complementary logic. Pass complementary logic. Okay, all right. Okay, I want you to understand the concept of the floating. Okay, this is to pull the output all the way to when we are not charging the output, right? And that will avoid for me a floating output. Okay. Typically, it is faster because you are going through NMOS, um, but it has more area because of this number here, 40 transistors, as we indicated earlier. Okay, so now we go to the next circuit. Okay, the next circuit here, these are dynamic circuit, and as we have learned from DIC class dynamic circuit, they have a clock here, okay, connected to a PMOS, and then you have this type of logic, okay, and in dynamic circuit, we know that they are faster, but this is the problem, they are power hungry. Okay, and here you can see that we are generating again also the output C out. This is C out. This is considered C out prime, by the way. C out prime, and the C out. Okay, and the sum prime and the sum. Okay, so after the inverter, we know that we always need a static inverter to avoid the problem of certain input transitions. Okay, so that's why we have this output inverter here. Now, obviously, here is C out, and obviously you have to generate here C out. Okay, so C out, and before the inverter, it will be C out prime. And you can easily trace the logic. For example, here I can check the logic here. For example, what is the logic here? It is A, B, okay, plus C, A or B, okay, all prime. Okay, so A, B, A, C plus B, C. Okay, and obviously this is C out prime. Okay, so and you can verify this as well here. Okay, so here C out for this node is what? It is A, A prime, B prime, or C prime, or A prime, C prime, or B prime, C prime. Okay. Now you can verify that this is the C out signal. Okay. And so if we go to quickly to the white. Okay, let's continue on the slide. No need for the whiteboard. So what we said here is that this node here, which is C out, it is equal to A prime, B prime, uh, B prime, or A prime, C prime, or B prime, C prime. Okay, and if we draw the K map here, let's draw the K map quickly. Okay, and this is here the A, B, C, change color here, make sure things are clear. Um, so, oops. Mm, let's choose green here. So 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And of course, this A prime, B prime, A prime, B prime gives me zeros here. Okay. And notice I'm saying zeros. Why zeros? Because this when A prime, B prime is on, right? I will discharge. Okay. I will discharge because notice that the dynamic circuit has two phases. First phase we charge up to VDD and then we discharge conditionally based on the value of the inputs. Okay. Now A prime, C prime, A prime, C prime. There is a zero here and a zero here, and then and C prime, B prime, C prime, so zero. So we conditionally discharge here, okay, with these values. The rest of the values are one. It's one, 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 and these are the C out value. Okay, so that's your C out here. Okay, all right. You can do the same analysis here with the sum and sum power. We said here this is sum. Okay, yeah. Notice one notation he's using. The signal he's using the active high signal is with the H. And this is non-inverting. Oops. This is non-inverting. The inverted signal he used underscore L. So underscore H underscore L. Very confusing notation, but anyway. Okay, so this is here the sum prime. Oh, that's not what I want to do, obviously. Okay, so here is the sum prime, and here is the sum. Okay, and he generates all these logics over here similarly. So this is typically fast circuit because it's dynamic, okay, but power hungry. Okay, takes 32 transistor, not very compact circuit, has a major disadvantage of power dissipation because of you are constantly charging and discharging the power circuitry, and that's why in the today's technology where everybody is looking for low power and low energy circuit, such circuit is not really very attractive for designers. Okay, all right. So to sum up, you have seen for the adder how we have progressed from a high number of transistor design when we have uh, no optimization 74. Then we said, okay, let's do a little bit of optimization here. 32, a bit more of optimization, 28. If you don't need the inverter, we can drop it to 24. Then we have seen the 24 transistor using transmission gate. We went to pass gate for up to 40 transistors, but we generate the function and its complement. So you can say, yeah, roughly we need 20 transistor per logic. Okay, 20 transistor per logic because we're generating almost double the circuit here. One some C out and some prime and C out prime, and then we went to 32 transistors when we have the went to fast circuit uses dynamic, but unfortunately it's a power hungry. So that's a survey of what one bit adder design is for, and typically, as I said, what is winning nowadays is low power, low number of transistors. Okay, thank you very much.